Okay, let's try to establish the safety of Gauss's method. The idea is that the safety of Gauss's method, this means that we want to establish that doing the row operations involved don't introduce any new solutions and don't lose any old ones. Okay, because we're after a general result, we can only rely on general definitions of all the relevant concepts. So let's review those briefly. So here we have the definition of a linear combination, and it is the sum of terms, each one of which is just a number times a variable. And we use the linear combination to make a linear equation by putting the linear combination on the left and setting it equal to a constant. A linear system is just a list of linear equations. So we have 1, 2, up to m linear equations, and each of them has to have the same number of variables, x1 to xn. And I have to sort of introduce an extra label, 1, 2 through m, 1, 2 through m, and then 1, 2, up to n to label the n variables in each equation. And this has a solution, a set of values, or list of values rather, S1, S2 up to Sn, that solves this system if you substitute S1 for X1, S2 for X2, Sn for Xn, and that makes all the equations true. Now, Gauss's method involves 3 operations and is restricted to those 3, called elementary row operations or row operations. And these 3, you can perform one of 3 operations. You can swap rows, interchange any 2 different equations. You can multiply a row by a scalar that's non-zero. You can combine 2 rows. You can add a multiple of 1 row to another row. Okay, so here's the theorem. The safety of Gauss's method. If a linear system is changed to another by swapping one equation with another, or multiplying both sides of an equation by a non-zero constant, or replacing one equation with the sum of itself and a multiple of another, then the 2 systems have the same set of solutions. This theorem involves 3 independent claims. So a proof is going to involve a separate proof for each of the 3 cases. Let's start with the first row operation, swapping rows. Okay, here's our strategy, or our first strategy. What we're going to do is we're going to give names to the relevant objects in the definition of a linear system to enable discussion. Okay, so here's our linear system, and we've given the name E1 of x to the first equation, where x is the name of the tuple x1 to xn, and so EM is the last equation, and we've singled out the 2 that we're going to swap with EI and EJ. Now, I and j are typical or arbitrary integers between 1 and m. So we're not going to use anything special about those equations. And because they're typical or arbitrary, anything we can prove with them will apply to all the indices between 1 and m. Okay, so a tuple of values S equals S1 to Sn solves this system if substituting the values for the variables makes each equation true. Okay, this is equivalent to the statement that S makes the following proposition true. This is the take-home piece here, that the wedge here indicates logical and it says both E1 of S has to be true and E2 of S has to be true, up through EI of S has to be true, then on to EJ of S has to be true, and finally EM, the last one of S, has to be true. So this just makes the claim that S solves all the equations at once. So our plan is to compare this claim with the analogous claim for the row swapped version and show that those 2 claims are logically equivalent. That means they always have the same truth value. The order of the single equation claims in star, that's this equation here, which is expression, that is, which is an expression repeated down here. So star is just this left-hand side here. And what we want to do is we want to transform it into the right-hand side where I and j have swapped places. And we can do this because of a property of logical and or wedge. for any propositions P and Q is logically equivalent, that is, has the same truth value as Q and P. This might be true, and if this is true, this is true. If the left-hand side is false, the right-hand side is false. Let's apply this repeatedly to star, this hand side. To interchange them, you can see I can sort of move EJ along to here, then move EI up to this slot, and I'll produce this equation here. Now, this process is, to make it precise, you actually have to do a proof by induction. But this is a result from logic, so we're accepting that as a already known result. It produces the general interchange equivalence, which is true for any list of M propositions. Okay, well, the claim that S solves EIS switches places with the claim that S solves EJS. Now, this equivalence shows that any solution which solves the original system, this claim over here, also solves the row-swapped version, the claim over here. And any solution of this, anything that makes this true, will also make this true, because these have the same truth values. Okay, so the original theorem was stated in terms of solution sets. So let's look at that. The solution set for S original is the set of all the x's, that's all the n tuples of variables, such that this is true, where I and j are here. Well, we just saw that this expression is true whenever this expression is true, so I can replace the first one with the second one. But this second one is just the condition for being in the set of the row swap. So the two sets are equal because they have essentially the same condition that defines the set. Okay, it's important to recognize in proofs like this what patterns are involved are. That's the value of this, as well as following the precise steps to know that it's true. And we looked at 3 cases, and we replaced a concept, linear system, solution, with precise definitions, and we gave names to the relevant elements to enable discussion here, especially EI and EJ, because the 2 rows that were being swapped. The form of the proof is a direct proof. We're just stating a logical equivalence or finding a logical equivalence, and that directly gives us the result. And the last one is that we're in the top of this slide, we're using this explicit definition of the solution set in which the explicit claims occur. So there's very little here except for organizing the result. And that's about it for this case.